here today to introduce you to Antonio Garcia Ferrer, in case you don't know him. This is a great pleasure for me and a great honor. Probably most of you know Antonio already, but in case you don't know him, Antonio got his bachelor's degree in Spain in '73, and then he went to the US. He got his PhD at the University of California at Berkeley in '77. He came back to Spain, but in '84, '85, he went back to the US, to the Graduate School of Business of the University of Chicago, visiting Professor Zollner. And he has been doing signal extractions for years and years and years and years. I don't want to tell you how many years I know Antonio, because then I will be confessing my own age, but he was already doing signal extraction. And he has been doing that, decisionalizing, well, not decisionalizing, he likes to work with raw data that include seasonality. He doesn't like the seasonalized time series, but I guess he, better than me, will deliver the message that he wants. He has contributed in seasonal extraction, for instance, with proposing the linear version of the dynamic harmonic regression models, and he got a lot of experience here. He has been contributed for the IAF in many ways. He has been first director of the IAF, then he was the president of the IAF, and in 2018 he got elected fellow. So I will ask you to join me to put your hands together to welcome Antonio. Antonio, the floor is yours.
Good afternoon, everybody. Let me just say how thankful I am to the organizers for inviting me to address this talk. It's supposed to be for practitioners. My first thoughts are about Laurent and Motion, who gave me the opportunity to address you these questions. The first time I came to the International Symposium for Casting was in Amsterdam, as early as 1988, where I presented my first paper. Then I have a small loss, and I came back in Stockholm in 1994. And since that day until Thessaloniki, I've been presenting papers here in the symposium for about 26 years. And I presented a total of about 35 or 40 presentations. So the ISF is my home. I feel at ease here. And I retired from the university a couple of years ago. And probably this will be my last talk at the ISF. As such, I organized the ideas about this talk as if it was my last lecture to my students. And what would be the message I would give them after so many years of teaching? And some of these ideas are the ones I would like to talk to you today. The time is not the best one. We used to hate when we were assigned to give the last talk of the afternoon, because chances are that all of you will fall asleep in a few minutes. So don't worry, I don't blame you. I will probably be doing the same. But see if you can find any interest in the ideas I will try to communicate. Okay, without any more preamble, let me talk about, I have divided my talk in 4 parts. 40% of the time I will be talking about seasonal adjustments and the dangers of seasonal adjustments. And also I'll talk a little bit about the problems with auto filters. In a third part of the talk, I will try to convince you how dangerous it is to use deterministic trends when you deal with the economic time series or any other time series. And finally, I will make you or I will present a very small exercise of a very successful forecast using very simple models regarding the COVID. Okay, so the problem with seasonal data or seasonal adjusted data is among the different alternatives, which is the optimal seasonal adjustment to use. Okay? As you probably know, there are many alternatives in the literature. So also there is not a theoretical model that we can decide upon. So certainly the decision is basically empirical one. So if this is the case, the question is do we have sensible statistical tools to discriminate among the different alternatives? Having in mind that we are using estimated variables, variables or components, we have to have in mind that those are not directly observable. So normally when I get engaged in considering different alternatives, I like to pay attention to the other components. It always worries me the idea of what happens if those components are not orthogonal. Because logically, when we think about different components in a classical decomposition, we tend to think that trend is different from cycle and different from seasonal component. But the truth is that normally this is not the case. There seems to be some correlation among the different components. So if the property of orthogonality is not fulfilled, then how this is going to affect our components. Okay. I was raised on the time series literature with the idea of how important it is to understand the properties of a univariate time series. And I learned, and I try to teach the same principles to my students, how important it is to take care of outliers and also intervention analysis using for certain topics that are not included in the real-world behavior of the series. So let me then start very briefly telling you how is the traditional approach. Well, you can see on the screen is just the sum of the trend, the cycle, the seasonal, and the noise. And the first thing I want to show you is a small empirical exercise where I include 4 time series, seasonal time series, that belongs to our leading indicator variable that we have been analyzing to predict the Spanish economy for a long period of time. So I'm going to be showing you results from the 4 elements of our leading indicator variable that includes car registration, housing starts, cement consumption, and trucks. Originally, I'm presenting the data that ends in 2013, but I have the results for this year not included in here, and the conclusions do not change at all. Okay, that's the way I like to look at the time series. This is very informative for me. As you can see, the 4 series are characterized by a non-stationary behavior in the trend, and very heavy seasonality in all variables. Also, it is quite evident the fact of you can see the effect of the 2008 recession that affected most variables, not only in Spain but everywhere. So far, that's what we see. Okay. So what happened if we use several model-based signal extraction? That I'm going to be using 3, but there are other alternatives that you can use if you want to look at it. Basically, Seeds and Tramo, which is a very well-known signal extraction method that was developed by my friend Agustin Marabal, the X12 ARIMA, and another alternative we have developed based on the dynamic harmonic regression of Peter Young. And what we did was trying to linearize this software and make it easy to deal with regarding this. Okay, I take for granted that all of you have heard about Seeds and Tramo and X12. So let me give you a very brief introduction of how the dynamic harmonic regression works. I think there's... Okay. Basically, the model consists of several unobserved components that we can, including the zero mean component of the noise. And this SJ include all the components you want to use. They are oscillatory, and they are represented here as a sum of sines and cosines. W are the frequency, different frequencies, and the C, and the interesting thing is both A and B are not time variable parameters, okay? So they change with time, and the most obvious value of W is W equal to 0, that corresponds to the trend component, and the model is fitted in the frequency domain. Let me show you one interesting characteristic of this generalized random walk. The main intention through my talk is to make you aware that many times you have to make decisions regarding the trend model. So the interesting thing is the GRW, the generalized random walk model, comprises many alternatives in the literature, okay? Not only the random walk, but some of the interesting alternatives are the integrated random walk, or the smooth random walk, or the local linear trend, the damped trend, and others, double integrated, many acronyms, so not very interesting. But it's important to understand that depending on the type of data and the periodicity, some models seems to be better than others. Okay? I won't tell you exactly how many, but that's the issue. So the DHR works very well. The software is very easy to deal with, and the only information you have to provide to the computer is the periodicity and the length of the series. And the software will automatically identify what type of generalized random walk, and if it's smooth random walk, they provide estimates of the parameters without any further problem. Okay, so I won't say any more about the dynamic harmonic regression model. And there you have the 3 seasonal factors that we have obtained using the 3 different packages. Okay? So if you look carefully at the seasonal factors, well, they look like seasonal factors. They look like the type of seasonality you are used to find out when dealing with economic time series. So if I ask you which one do you prefer, you will probably are unable to say this or the other one, because they look very, very much the same. That's it. So let's look at the seasonally adjusted series. Again, using the type of software that I described. The red is DHR, the blue is SITS and Tramo, and the green is X12. And again, if I ask you, do you have any preferences to choose among the three of them, you will probably have the same doubts as I do, and you will be unable to decide which one is your preferred time series, seasonally adjusted. Okay, so no way of discriminating, looking at the seasonal factors, no way of discriminating, looking at the seasonally adjusted data. So it occurs to me, well, the first thing you learn in time series is not to believe anything. Just trying to prove everything, to be convinced by the evidence. So let's have a look. Well, I hope that all of you agree with me that the series shouldn't have any clue or any sign of seasonality left, because the seasonality has been already removed, okay? So let's see what happens. Okay, this is the autocorrelation function of the three methods, the seasonally adjusted series of car seasonally adjusted registrations. On top, you have the DHR autocorrelation function. In the middle, you have the SITS and Tramo, and at the bottom, you have the X12. If you look carefully, it will strike you how there seems to be some evidence of seasonality left around 12, 24, 36. And the same with X12, 12, 34, and 36. So it's funny. So are you telling me that using a time series, which I believe was to be seasonally adjusted, but the truth is there is considerable evidence of seasonality left? Okay. So you may wonder, what happened with SITS and Tramo? Why SITS and Tramo doesn't seem to have any evidence of seasonality left around the seasonal spikes, 12, 24, and 36. Why SITS and Tramo seems to be much better than the other two methods? Remember that normally, if you are used to using big, large amount of data that are supposed to be seasonally adjusted, I'm sure it didn't occur to you that you may be facing this problem. If you're facing this problem with how many time series in the whole set. Okay. There's one very important reason why SITS and Tramo do not have a similar problem. Because in SITS and Tramo, there is an automatic option that takes care of calendar effects, Easter effects, and many other effects in your country that is taking care of this. Okay? So, as a matter of fact, my first summary of tentative results of these 4 series, by the way, I am presenting the cars registration, but the other 3 have exactly or very similar results. Seasonality is left on the seasonally adjusted series. So The good thing about studying univariate time series is you get very well disciplined regarding how certain properties need to be fulfilled. And the presence of Easter effects and calendar effects in the estimation of an observed components is very important. As a matter of fact, had we used seeds and trauma without these automatic options, we will be finding exactly the same results we are finding in the other two software. And again, very strikingly, using outlier detection and the presence and checking the presence of Easter or calendar effects produce a considerable reduction in the estimated residual variances. In this particular case, for the 4 variables, reductions are from 21 to 31%. Huge amounts. So that means noise in the series are going to be there because you didn't remove it. We don't know what happened with the others, with the other series, but this is a very important factor to having into account when leading with this type of series. Okay, is this a particular result that is only to be found in the Spanish time series? Well, the answer is no. And I use a small number of series from the famous Stock and Watson database, particularly housing starts, industrial production index, money supply, and retail sales. Stock and Watson are changing the base from time to time. Originally it started when 126 series, and now I think the number is 250 something, or probably larger. I have been using the database for a while, so I don't know exactly how many variables are in there, but it's a large number of variables. Okay, see if we can find similar results as we found in the Spanish time series, okay? And there you have the 4 time series, those are already series without seasonality. So you have, So you have houses, which obviously is, it seems to be a stationary time series, and then you have the other 3 time series that behave as we expected, non-stationary behavior, and the same with retail sales. Okay, so look what happened to the autocorrelation and partial autocorrelation function in the case of the housing starts. Again, we were not supposed to be finding this, the presence of seasonality in the series. And if you look at both at the autocorrelation and partial autocorrelation functions, what you have is, again, strong evidence of seasonality left, both in the partial and in the autocorrelation function for the housing starts. The same happened with the industrial production index, both evidence of seasonality left here, in here, and a little bit in there. The same in the money supply. Again, similar seasonality around these 12s, and a similar case in the retail sales. Okay? So it seems to me that the results we found first for the Spanish economy are not unique. So what? That's the question I can ask. Well, I cannot tell you. I have not investigated what would happen if in a large number of time series, which were supposed to be seasonally adjusted, seasonality is left in many of them. To tell you the truth, as I said, I don't know the consequences, but I fear that some of the results may not be known, particularly if you try to build a large econometric model or a large factor model, the interaction of all these things. Why do you think, or why do I think these things are happening? Why is such a strong preference in the econometric community and macroeconomic community to prefer seasonally adjusted data? And I haven't checked this point of view with anyone. So I'm a little daring to say that in public, but since I'm retired and that will be my last talk, who cares? I have the feeling that seasonality is creating an additional problem in the modeling process. Actually, when I have worked with my co-authors in several forecasting projects, and I remember carefully one we made about traffic transportation in Madrid, public transportation. And we developed some interesting, very accurate models, and then suddenly we start failing miserably in the months of June, July, and August, in the summer. So what was happening is simply that habits were changing, and the fact that summers are associated with very idle times where people move on vacation, the whole month of July or the whole month of August is no longer the case. So it is clear that seasonality is also non-stationary, and in a time series, particularly in multivariate time series, having to deal with the seasonality problem or deciding that we can use deterministic seasonality is much easier. So what is very easy is to take for granted, suppose that we don't have seasonality. Well, we have one less problem to worry about. But anyway, that's only my thought, so I'm not sure whether this is true or not, but I would like, when I made a comment to Mark Watson in Madrid a couple of years ago, Mark is a very sharp fellow. So he looked at me and said, well, I think we should congratulate people who devote their time to seasonal adjustment. They are doing a great job. Well, what else can I say? Okay, so far, I will not talk anymore about seasonal. Let me talk about other filters in econometrics. Okay, this is perhaps the most famous filter in macroeconomics and macroeconometrics, which is due to Hodrick and Prescott. If you were old enough, you probably realize that the original paper they wrote was in 1981, and it was so highly cited by a large community that I never understood why it was never published. The paper is, as I said, it worked as a working paper, and finally, I think it was the Journal of Credit and Banking in 1997 was finally published. There are a few very small differences between the two papers. The 1981 database ends around 79 fourth quarter, while the second paper was a much database. The length of the period was much longer, and it started in 49, and I think ended in 1996. Well, thanks to a colleague of mine, thanks to Pilar Poncela, I found out that in the engineering area, they don't know this filter as a Hodrick and Prescott, but they know it as a Whittaker filter. So Whittaker, and I had the paper, and Whittaker developed, Whittaker with someone else, developed the same exact filter for dealing with actuarial data. But to be honest, with Hodrick and Prescott, they recognize that in the original paper, so they are not attributing themselves the merits of having discovered a filter. So the basic idea in the filter is that lambda is a parameter that penalizes the smoothness of the trend, and basically lambda is the key parameter in this approach. Okay, so the interesting thing is why lambda equal to 1600? Okay. Hodrick and Prescott justify this value of lambda because they made assumptions about how the two variances, lambda is the ratio of the variance of the short run, the variability of the short run component in the cycle, and in comparison with the variance or the variability of the long-term components. And they, without any reason easy to understand, the ratio was assigned about 5% in the short-term components and about 1 divided by 8 in the long-run components. And the variance, lambda is the square root of this ratio, 5 divided 1 divided by 8. Okay. So two striking things. Many econometric software included Hodrick and Prescott as an alternative. And so people in the macro area, particularly in my university, all the macroeconomists were applying lambda equal to 1600, and they thought that the Hodrick and Prescott filter was the panacea to solve all the problems in filtering economics. So what I found out is not only that lambda was equal to 1600 in the case of the US quarterly data, but also if you try to disentangle a little bit the frequency content of this value, you discover that the value of lambda corresponds to an average cycle of 5 years, which was, by the way, was exactly the average cycle of the US economy. But the business cycle history of the United States has nothing to do with the business cycle history of Italy, Spain, England, Japan, and any country you may have in mind. So people took this value as people have information about the the 9.8 of the gravity law. And people were using lambda equal to 1600 for any country, any periodicity, any length of the series, and surprisingly obtained the cycle of using this decomposition, and they are very happy with the cycle. Okay. To be honest, since the very beginning, the Hodrick and Prescott filter had many defendants, but many enemies. I can name 2 or 3 economic Nobel Prizes that they didn't like it very much. So, but probably to be fair, if you have in one hand those in favor and those against, probably there is a balance. I'm not sure, but probably. I've seen many reports in both directions. Okay, perhaps the most interesting paper regarding this is one recently published by Hamilton that he called it, "Why Should Never Use the Hodrick and Prescott Filter." So Hamilton is quite straight. He's not worried about political correctness. So the paper is very good, by the way. And he presents some evidence of why at least the use of Hodrick and Prescott blindly can distort the properties of very well-known US quarterly or monthly time series. So if you look at figure 2, you have the autocorrelation and cross-correlation for the first difference of the stock prices and real consumption spending in the case of the US. And what we found was something that has been confirmed by many other researchers in the area for years. 15, 20 papers, maybe more, that I can recall. So what we're expecting basically is the behavior of something that could be considered a random walk. First, in both series, both in the Standard & Poor's, we have the autocorrelation with some lag. So if you exclude the zero lag, all else seems to be zero in both cases, more or less. And also confirms, using the cross-correlation functions, that there is no evidence of any potential causality from one to the other or vice versa. No? Okay, so this is very interesting because this is what we are going to expect to see when we present results, original results. Okay, what happened when we analyze the autocorrelation of the Hodrick-Prescott cycle for Standard & Poor's and for consumption? And as you can see up here, because of the artifact of the transformation, you have here something that is very surprising, seems a very well-defined structure in the Standard & Poor's, and the same in the consumption. And also, you seem to be happy because you try to find, using the cross-correlations, you seem to believe that there is a causal relationship between both variables, and probably in both directions. So it is very unrealistic not to be able to check these things beforehand and incorrectly trying to derive causality relationship between variables that they are truly a random walk. So the idea, if a very simple random walk is so distorted, what would happen with other type of variables? And also, And that's a very, I like this, the next picture very much. This is, as you can see by the quality of the figure, that this is quite old. And it was at the beginning when Hodrick and Prescott filter was being used by many people, in particular, as far as I know, in Spain, but in other countries too. That's the cycle you get for the Spanish GDP. Okay? And as you can see, because at the time that the value of lambda was imposed, you get different alternatives. By the way, I just forgot to tell you, in the Hamilton paper, what Hamilton did was estimating, using maximum likelihood, the values of lambda for a large number of US series. And strikingly, the estimated values range from 0.9 in the case of employment to 0.3 to 9.2. So the largest value of lambda was 9, very far away from 1600. Anyway, so there you have, these are very old papers, I said, but the message is very important to me. You have several alternatives. As you can see, this is the value for 1600, you have 400, you have 500. And then you have the implied cycles obtained by using these values. Okay? So, what is a striking thing about this figure? If you suppose you know nothing about econometrics, you know nothing about filtering, you know nothing about practically anything, but you know how to read a graph. You would say, suppose you are a historian and said, and you know a little bit about the history of Spanish GDP, and then you are very naive and you ask, so according to these results, this is from here to here. These would be typical characteristics of a trough in the business cycle. So which means negative growth, right? And you say yes. Well, it happens that during that particular period, Spanish economy was growing at 4%. So it's not only that it distorts the basic properties of the time series, but also in terms of policy, could provide terrible results. So because your historian friends would come and say, listen, this doesn't make sense. So very silly results. You are an idiot, because you're telling me that that's a trough of the Spanish GDP, and I know by the data that Spain was growing at 4%. So, again, a warning note that you should be very careful when using the Hodrick and Prescott filter. I'm not saying don't use it. You can use it because it's not a bad method to obtain estimated trends, but you must be very careful, and actually there have been many papers advising not to use lambda equal to 1600, irrespectively of the periodicity of your data. And I think it was a paper by Rao and Van in 2002 that gives you a larger range of plausible values of lambda. Okay, that's end my second part of the talk, according to the filter. And let's move to another issue that is very, that I found interesting to me, sorry. I hope it's interesting for you too. Okay, this is a very old time series, by all means, very long, that includes data from 1659 to 2007. This is a time series very well known by people in climatology. And that's the central England temperature comprises a triangle that includes Bristol, I think Cambridge and London. And according to the climatologists, it's very important because it reproduces many interesting results. And this is a blessing because, as I said, we have data from 1659 to 2007. This is annual data, but if you are interested, they have the data has been under revision for several years, and as far as I can tell, revisions have been very good, and this is a time series that you can rely on, very accurate. At the time, you have data on a monthly basis, and you have daily data already. The daily data does not go as far as the monthly or the annual data. Okay, that's the data that we saw, and the red line is just the mean of the temperature. As you can see, well, in another graph that I'll show you later, of course, the mean has changed. Okay, what is interesting to me is that you pay attention to the alternative different cycles, and I will explain what the Bayesian turning points implies. Okay, this is the different cycles obtained by using different NBRs. The NBR is the inverse of lambda, and that's a result that Peter Young and Jakeman proved in the late 60s. Okay, and as you can see, by using different NBRs provides length of different amplitude. They overlap, of course, but as you can see, the yellow is the color. The yellow is the color corresponding to this particular value of, let me say, is 510 to the minus 4. But anyway, it's interesting to see, well, the largest point in the cycle is around 1705 or something like that, which is here. And all of them, are going to pick up this value, which is, it was just not the Industrial Revolution had started. So, and at the end, you see there are many cycles. One of the largest cycles is 80 years, but there are many cycles in there, which I think is very, very important to analyze carefully what the data are supposed to tell you. And these vertical lines, corresponding to about is where the Bayesian detection algorithm named as a turning point. This algorithm was a paper we wrote with Elias Moreno and Javier Girón. And it's funny because we work separately. They haven't seen the cycles that I have developed, and they check 3 important turning points. One is 1699, you have the 1739, and the last one I think is 1960. That's the result we have when we finish analyzing these results in 2008. So that's why the last year we analyzed was 2007. So what was the model telling us around 2007? That was supposed to be the expected growth rate of the temperature at the end of the year. So it was a small up, down, up, and then as a characteristic of the filter, we have this kind of value at the very end. Okay? So we couldn't say much, except that we were trying to tell, watch out with your trends. So when I was coming to the meeting, I just enlarged the sample data, and now the sample data ends in 2023. And the DHR algorithm suggested this model, suggested the model with this smooth random walk trend. We estimate the value of the parameters, but we had the freedom to force other alternatives if we want to. Okay, so what we did was estimating another model using an integrated random walk trend. As I said before, you can use any trend that you consider to be good for the issue. By the way, in terms of fitting, both trends fit very well. So fitting is an interesting consideration, but it's not the crucial one. What was crucial or very important is, okay, what message for the future provides using one trend or the other? Okay? And that's what we got. What we got is two very different messages for the short-run behavior. If we decided, I mean, and then you need to, if you have a strong preference for one or the other, then if your preference is that things are going very bad, then you will be very happy with this one. With forecast behavior, this is going to be very negative in terms of increasing the temperature. But if you think that, well, things seems to be smoothing out a little bit, easing out a little bit, then you will go for this one. So the question now is a moral question in terms of how results should be presented. From a scientific point of view, you must have very clear in your mind whether you want to persuade or to inform. If you already have your priors regarding which school you are in favor of or which thought you're in favor of, then you may choose one or the other. But you might be not behaving very properly. If you want to be a good scientist, you should provide all the information available, and you have to check all the alternatives available. And as you can see, trying to use a linear trend with something like this, it would be a mistake difficult to accept. Okay, so let's move to another topic. I don't know how much time do I have? 5 minutes? Really? Good Lord, I thought I didn't have time. Okay, so let me just, I will be a little bit fast. This is a very interesting issue because It includes yes, a paper that was recently published by Peter Young and his colleagues relating the global temperature. Let me see. Okay. The changes in the globally average surface in the temperature. It is very important that you read carefully these two definitions. Okay? A positive anomaly indicates that the temperature was warmer than the reference value. And here, and that is even more important, this is the Atlantic multi-decadal oscillation, AMO, and the definition, it is very clear. It tells you exactly what you're looking at. Variability in the North Atlantic once a linear trend has been removed. And he said, this trending is intended to remove the influence of the greenhouse gas-induced global warming from the analysis. So they are telling you that this series is not the original one. It's just the series without a trend. Okay. Originally, what Peter Young found was that the two series have a common a common cycle of 63 years. So what we've done is we tried to look this in the case of GTA, and there you have the original series here, and the trend, and up there you have the 60-year cycle in green and the 21-year cycle in red, and other harmonics. Okay. When you analyze the component for MAO, what we found is that the 63 years is not present. We only have the 21 years and other harmonics and irregular. So what happened when we compare the two cycles together? Well, it seems that the GTA has a periodic cycle, but not AMO, which in part contradict the results found in Peter Young's article. Okay, believe it or not, there existed an original AMO series. It was hard to find it, but we found it. Well, to tell you the truth, my co-author found it. So, what happened when we analyzed the original data, with the trend included, is that we find exactly the same decomposition as before. Okay? So 63 years, the 21 years, and the other harmonics. And when we now compare both, they have the common cycle appears clearly in the results. Okay. 2 more minutes. Thank you. So again, the lesson learned here is, please use your original data. Okay, now just a small empirical exercise, forecasting exercise that I made during the COVID times. All of you know what were the situation at the time. So I have several medical doctors, friends, who were very worried because they, at the starting point of the pandemic, the urgency services were being fulfilled. So they were afraid that they cannot cannot deal with the problem. So they asked me if I can provide any help in developing forecasting. So the problem was that we only have like 9 data points. And with nine data points, it's not very wise to try to do very sophisticated procedure to deal with. So the most helpful point, and also at the beginning, if you remember, everything looked like an exponential function. So my first duty was trying to figure out when the exponential will start looking like a logistic. So, but in this particular case, Italy, so thank you, Tommaso, Italy came to my help, because what we found out, look at Italy at the very beginning, is right there. Italy was about a week ahead of Spain. So in other words, Spain was reproducing results that happened in Italy 1 week earlier. So that's the situation, and you will see Hubei, China, which very soon became unbelievable, the results, and you have Italy and Spain. And so what I did was I built a very simple transfer function model where I include the lags of the Spanish diseases and Italian data as a leading indicator. And I remember those days were very exciting. For the first time, I felt useful for the society, for the community. I was able to provide some help. And that's the behavior, the forecasting behavior. These are not all-time forecasts. So what I did is I made a week forecast, then I introduced this data, and I make another week forecast, I introduced this data, and I made a week forecast, and so on. So it was very helpful. It was very accurate, sorry. And I was feeling, as I said, useful for being able to provide these results to the community. Okay, I had some conclusions, but I think I'm taking too much of your time. I'm surprised that you stay the whole time here. So many thanks for attending the session, and I'm happy to answer any question that you want to make if you want to make it. Great, that's it. Thank you very much.
Take the microphone.
Easy, please.
It's on. It's on.
¿Funciona?
Yes.
Okay. Okay, first I want to thank you for this revision of many things that we have been learning for many years. It has been great. And I have to say that I am very happy to share many of your views, although I don't share many of them also.
That cannot be expected.
I don't think it's the moment just to discuss. We have been discussing for many years now, and we can keep going for many years. So I am also happy to say that I am happy to be your friend, not only to discuss about...
Sorry, I didn't hear you.
To be your friend, not only to discuss our research.
Of course.
So, being said that, just a couple of comments. And one is about one problem that you know that I am very worried about is temperatures and forecasting temperature, where we are going. And with respect to the two alternative models for the trend that you show us, why not to put some kind of uncertainty around? I mean, you just put like point estimates of the trend. So I think it's also important to say what we don't know. I mean, our models have uncertainty, and maybe having this uncertainty around can also be useful to know whether, I mean, we can say about the future or not.
Well, I am certain too. I'm not saying that IRW is better than smooth random walk or local linear trend and so on. What I'm trying to show you is the uncertainty associated when estimated one or the other. And I don't see clearly how can you associate probabilities with this result, because in terms of statistical fitting, results are very similar. So what I'm saying is, rather than openly saying the situation is getting much worse, there's going to be an increase in the temperature and so on, or to say, no, I think things are easing out a little bit, and it looks like maybe the beginning of a downturn cycle. I don't know. Using this information. I don't have any other information. So maybe we are able to assign probabilities and we can write a very nice paper, yes. But all ideas are yours. I have none.
Thank you. In a first course on time series analysis in a bachelor course, do you recommend to still teach on Hodges-Prescott filter, seasonal adjusted series? Or, I mean, do you recommend that we need to stop teaching this kind of stuff, or what? I'm particularly asking because I'm teaching in Mexico. I need to teach the first course on time series analysis. So, yeah.
Well, the Hodges-Prescott filter is dangerous only if you don't know what you're doing. If you know very well that putting the same lambda value to all time series is a tremendous mistake. But given the similarities with other extraction, observed component model extraction, I always find very easy ways to use one or the other, because sometimes, as I said, lambda, the NBR in the dynamic harmonic regression, which is the smoothing parameter, by the way, is 1 divided by lambda. So sometimes we can reproduce results from other areas, other filters, but you need to be careful. You need to understand what you're doing. You need to understand what the implication if you assign a particular value of lambda for the expected business cycle. So I'm not very much against the Hodges-Prescott, but it's very dangerous, like giving a gun to a child. They can shoot their feet. So you have to be careful. I don't know if you're a hunter, but if people hunting without any problems because they know how to shoot a weapon. Thank you very much.